Hi everyone, I hope you are well. Today I'm going to discuss about my research of interest, which is actually uh, is a kind of studying charge transport in molecular junctions. One usual doubt I was getting in this field, and also through like whoever comes to this field, they will get this doubt, which I will explain in this presentation, and a short intro about what actually in the main theme or theory behind or what we actually do. I will discuss in this presentation with a article reference. So let's start it. So first I will explain about conductance and attenuation factor. If you take a piece of wire which has length L, and if it has a cross section area A, then the conductance is directly proportional to the conductivity and its multiple of conductivity with area and divided by the length. It is inversely proportional to the length. If we have two factors like two times of the length, then your conductance even decreases. And if you have more, the conductance is gradually going to decrease. This is in bulk system. But if we go to nano system, this is the analogous equation for conductance in nanoscale systems. G is the conductance, G naught is the conductance at zero bias, and beta is the attenuation factor, and this length L is actually the size of the molecule. Since we are considering molecular junctions, and the conductance of molecular junctions is this. It's an exponential decay, whereas here it's inversely decay of conductance. And if I rearrange this equation, we will get a linear kind of equation if we consider, and the slope of this equation is this one minus beta, so it will have a slope is minus beta, so the graph looks like this. It's a perfect straight line with decay in a negative direction. The slope is minus, so straight line with a negative slope. And if you consider perfectly vacuum, the vacuum has a constant of beta 25 nanometer inverse. So this means for a nanometer length, 25 units of conductance will go down. This ratio will come down. And if you take a perfect conductor, which is a metal, thus its conductance versus length plot is straight line. It will give, there is no decay in the length of the conductor. Like if you take lattice, how much distance length if you increase repetitive unit cell, its conductivity won't change because it's a uniform potential, and electron experiences uniform resistance only, whatever the unit length. So if you get a graph of any molecular junction in between these two, then it's actually from our material. Any metal or between conductor or insulator, their beta conductance plot looks in between these two values only. And for if you get a positive slope, meaning it's actually even conducting more there is no decay, actually it's actually inverse for conductance. As your length increases, the conductance is actually increasing, which is actually a peculiar way, which is actually weird. Usually if you see in bulk, what actually it means is like if you increase length, actually the conductance have to come down. But in nanoscale junctions, we were seeing a behavior of this. I will explain this result later, but but I feel that I had given understanding about the conductance. So actually the one main question everyone will get, one doubt everyone will get is when a molecular junction forms, is it the charge transport between molecular junction, is it from molecule or is it through bond of the molecule or through direct space itself, because there are two chances. It can go to through space itself, and or else it can go through the molecule. This is the molecule, it is sandwiched here. So how can we know? The length of the molecule is actually in order of nanometers and very small, and if we apply bias, it can have two fate. Electron will have two fate. It can go through the molecule, it can go through the space. So how can we know that? Let's keep this aside. The one application of this molecular junction is actually in electronics. If we decrease the length of the, let's say, these transistors whatever are in currently electronic devices are carrying, their size is getting down. Their size is getting even down such a way that this tunnel current will always be there. We cannot control this tunnel current, which is actually through space it comes. This is actually gap in between this order only. So how that will be a detrimental effect for the electronics. So how can we solve that? One solution is by introducing a molecule of interest. We can control this current if it goes through the molecule, which is, we have doubt is it through the molecule. We can control this tunneling current. How? I will explain. This result from this paper in 2019 reported that this is the conductance plot same as we got. It's a oligo of adenine ethylene molecule, and if we increase the units, whenever this straight line comes, actually this decay comes if it is a through space tunneling. Whenever our plot gets straightened, that is from molecular tunneling. This report has this conclusion has given by this article, and they had seen that you can see here the first oligomer unit has length of 1.1 nanometer, and they found the transition from through space to molecular is around 0.66 nanometer. And actually you can ask in between how that it is even smaller than this gap, right? So how it can give the current? Yeah, good question. But actually it can be bent, and it can be bent and attached. It cannot be straight also. That bent is actually with an angle of 35 degree, you can see. So they increased the molecular size. It went to the trimer is around 1.8, and tetramer is 2.5, and after penta units it is around 3.2, and its transition distance is this one, you can see. So by this conductance plot we can say actually whether our molecular junction is formed, or, and again that tunneling current is from molecular or not, we can understand by this plot. So you can visit this paper and read if you want. This everything is there in that, and I hope I had cleared out how to distinguish current through the space and through our molecule. If we do the experiment, which is called STM-BJ, which I will explain later some point of time, and when we get this plot, we can say that it's from our molecule, and as well as it's from the molecular backbone itself.